of IOs. And as you can see on the right hand side, as we increase the number of qubits, the number of microwave lines increases, and these numbers do not include, for example, DC lines for tuning and other lines for readout. And as you can see, the numbers explode as we go to larger number of qubits. And in fact, the IOs become the most expensive part of quantum computing, and the cabling from room temperature to millikelvin stages are very expensive, and they could be point of fault in our system. And as you can see, large input-output count kind of introduces scalability problem, and long wires introduces a latency problem. There are different options to bring all those classical control circuitry to the cryogenic environment closer to the qubit. So one of those approaches is using cryo-CMOS. Can work in cryogenic, but still CMOS dissipates a lot of power, which is not helpful in cryogenic environment. And those cryo-CMOS seems to be mostly suitable for spin qubits, semiconductor spin qubits, and not for superconducting qubits. And recently, Google team has developed some system, cryo-CMOS, that works at 3 Kelvin. The other approach is instead of using CMOS technology, use superconducting electronic. The advantages of superconducting electronic is that they are very low power, very fast, and especially the ones that is based on single flux quantum, which is going to be the base of this presentation. But the disadvantage and problems are that unlike CMOS, which has a high integration density, SFQ integrated circuits have lower density. And one other thing that we need to remember, that trying to mimic the conventional approach of microwave to quantum computing, trying to use superconducting electronic will not work well because of the integration density issue. So we need to come up with a new approach. So the other approach to scalable quantum computing is to use RSFQ technology. RSFQ technology is a digital superconducting technology based on Josephson junction. Josephson junction is the similar Josephson junction that used in superconducting qubit. Here I would like to give just a brief introduction of what RSFQ technology is and what digital quantum computing is. So a Josephson junction is made of 2 superconductors that sandwich around an insulator. And so in this 2-terminal device, the current can flow without any resistance up to some threshold. After that, this Josephson junction switches to resistive mode and shows resistance. The circuit symbol for a Josephson junction, as you can see, is like this across. So in this technology, how do we define 0 and 1 digital? In CMOS technology, 0 and 1 is based on the different levels of the voltage we have. If you have a high voltage, we call it 1, and if you have 0 voltage, we call it 0. And RSFQ technology, 0 and 1 are based on the amount of the flux that goes into a loop. If there is a circulating current and there is a flux inside that loop, we call that digital 1, and if there is no current circulating that loop, we call that 0. So in order to add 0 and 1 into our circuit to create digital 1 or digital 0, we put a Josephson junction inside a superconducting loop. If the Josephson junction doesn't switch, a flux is trapped here, which shows that this loop contains 1. If the Josephson junction switches, this flux can come out, leaks out, and this loop becomes, for example, 0. Every time that this Josephson junction switches, it creates a pulse, a very sharp pulse with a length of around a few picoseconds and with a small height. But the important things about this pulse is that the area underneath this pulse is a quantized value. It's a fixed value, and that's because of the flux trapped inside inside a superconducting loop is always a quantized value, and because of that, the area underneath this curve is always fixed. So, for example, based on what I showed, we can create all the digital gates that we need. For example, we can create AND, NAND, NOR, T flip-flop, RS flip-flop, and all kind of digital logic that we need. For example, here I just show an RS flip-flop. That, for example, this if a pulse or a flux comes from the left, it switches these Josephson junction, and a flux is trapped here, which shows 1. So this RS flip-flop is now carry the state of 1, and if for readout, if we send a pulse, a signal comes out and read out as another 1. The advantage of the RSFQ digital is that it's super fast. It can work up to 350 gigahertz, and it's not only a digital logic, it can also be memory element too, because it can store the state, and it only uses DC bias only. There is no AC biasing, although it works up to 350 or more. It's only DC biasing, and it has many other advantages, and it's super fast. One of the other advantages of the SFQ technology is that we can send SFQ pulses through microstrip lines ballistically without any dissipation, and that can happen in the speed close to the speed of light, which is a big contrast to semiconductor industry, which the speed in VLSI is limited by RC charging type, which doesn't exist in superconductor. And the beauty is that we can match the impedance of the strip line to our Josephson junction, and one of the other advantages is that the crosstalk is very small in between lines, and the amount of dissipation of energy is very small. For example, for sending one SFQ pulse from one side to another side, it's in the order of 10 to the negative 19 joule, which is very small. Here I showed you an integrated circuit made of SFQ electronics, which is an ALU, and as you can see, we have developed Foundry to create integrated circuit for digital logic using SFQ. Now the question is that, can SFQ work next to qubits? At SIG, we've developed superconducting SFQ class circuits that enables us to fabricate SFQ digital electronic close to quantum qubits. For this, we've developed a new family of RSFQ logic, which are called energy efficient RSFQ circuits, which has zero static dissipation and very low dynamic dissipation. And also for reducing the dissipation, we've scaled down the critical current density of our Josephson junction. So for example, in ordinary SFQ technology that works at 4 Kelvin, we typically use Josephson junction, which has around 125 microamp, but for qubit application, we use 10 microamp or 10 microamp Josephson junction. We've developed high kinetic inductors for higher density of integration, and we've developed layouts that is aware of the qubits to minimize the adverse effect of classical circuit on quantum part. Now I'll explain how SFQ pulse can be used to control the state of a qubit. In conventional control of qubits, by shaping of microwave pulse and changing of the phase of the microwave pulse, we can get the state of qubit to anywhere on this block sphere. But in SFQ control, the way we do that is that we have a train of microwave pulses, which are very sharp pulses. As I mentioned, they're with a width of few picosecond due to the switching of Josephson junction. They come in time. The way we control qubit is that as qubit make a precision around the z-axis due to its natural frequency, every time an SFQ pulse is applied to the qubit, it kicks the qubit in the direction of the red arrow you can see. So we kick the state of Q pulse with this red arrow, and we let it precess one time, another kick, it precess another time, and till we get to the location on the block sphere that we desire. And as you can see, by timing the delay between the two pulses, we can get to different location on the block sphere. And how it's done in circuit, it's the circuit on the left. The left shows the circuits that create this SFQ pulses and control them, and the coupling to the qubit, which is shown on the right, is done through this capacitor. This capacitor, as I'll show later, is the capacitive coupling between the two chip, classical and quantum chip. And each kick, the rotation that we get out of each SFQ pulse is a fixed number, which depends on the value of this capacitance and the value of the qubit parameters that we have. It's also worth mentioning that these pulsars are quantized pulses, so all of them have the same shape and size. So the only parameter that we need to control is the delay between every two pulses, and that's the origin of the quantum digital control of the system. As we put the classical SFQ circuit next to our qubit, we can mitigate the adverse unwanted effect that the classical circuit might have on the quantum chip. As you know, the quantum state is very fragile, and we need to keep away any disturbance to the quantum states. But for doing that, we put the classical chip in a classical and quantum chip on a multi-chip module, where the one chip, as you can see on this picture, the chip on the bottom is the classical chip that does all the control, creating pulses, and for the readout, and the chip on the top is the quantum chip, which is sort of isolated from the rest of the the dilution fridge. We can use optimal control theory to optimize and maximize the fidelity of the gate operation. So without optimal control, the SFQ pulse that is applied to the qubit looks like the top row, as you can see. But by using optimal control theory, we can change the fidelity of operation to get the maximum fidelity. And how it looks like is like this barcode shape. And as you can see, if there is a space between the two pulses, it means that there is no SFQ pulse in between, and as get denser, there are more SFQ pulses going to the qubit. With that, we can maximize the fidelity of operation and also control the leakage of the quantum state to higher state, which is unwanted. And also by using optimal control theory, we can minimize the gate time to get which is important in many algorithms. I should also mention that SFQ technology can also be used in readout of the state of the quantum bit. There are different methods to do that. One way that I show here which was developed by at the University of Syracuse with collaboration with SEEK, was using JPM and JPM, which is Josephson photon multiplier, and SFQ for readout of the state of the qubit. And we are working on different method of SFQ, which is an active research. Being able to control a qubit and read out the qubit using SFQ circuit, this is how an SFQ-enabled digital quantum computer looks like. It consists of 3 loops, a fast loop, a mid loop, and a long loop. The fast loop, which is SFQ digital qubit manager, sits in proximity of our quantum layer at 20 millikelvin, and what it does is that it does the readout of qubit and control of qubit, and also it's able to do simple data processing. At higher temperature, 600 millikelvin or 3 Kelvin, sits our classical coprocessor, which can handle computationally heavy operation related, for example, to error correction or related to specific algorithm requirement. And at the end, in the long group, sits our interface to the room temperature computer and electronics, which is responsible for compiling the algorithm and interfacing to the world. So different algorithm requires different kind of feedback loops. So for example, some algorithm requires very low latency, fast feedback, which can happen here. Some algorithm requires medium delay, and heavier computation that can happen here, and longer delay can happen to the room temperature. So this is how the system looks like in cryostat. In the bottom is the classical quantum at 20 millikelvin SFQ classical coprocessor at higher temperature, and again the rest at close to room temperature. And between all these stages are superconducting cables that SFQ pulse can propagate between the stage of 3-4 Kelvin to the millikelvin, and from that part up, SFQ pulse cannot propagate, and it will be through a regular microwave connection. In summary, we have replaced a non-scalable analog microwave method of control and readout of qubit, which is used in conventional quantum system, using SFQ technology. And if I want to compare our digital approach to analog system in a table, I can say that clock speed is much higher in digital circuit. In SFQ, we can get 20-40 gigahertz easily, but in analog, the clock speed is limited to few gigahertz. And the power dissipation in analog system, even using cryo CMOS in the future, it might get down to milliwatt, but using SFQ technology, it's sub microwatt per qubit. And one of the issues that I didn't mention much was that the heat sink with using many cables is reduced considerably with SFQ technology. And the other thing is that with SFQ technology, the crosstalk and interference is much lower than analog microwave method. And one of the important things is the latency. And as you show in the architecture, we have fast loop and medium loop and long loop. We can have the feedback and feedback delay up close to picosecond and tens of nanoseconds, which is very important in many algorithm, but in microwave that's much longer in time. And of course the cost with the SFQ approach, integrated approach, we can reduce the cost significantly, which is also important in making a large fault-tolerant quantum computing. I would like to thank you for your attention and wish you
Hello, my name is Rubindra Das. I will talk about cryogenic qubit integration for quantum computing. But before I talk about quantum computing, I would like to give you two information. One is that classical computer does amazing things. Today's Internet of Things, artificial intelligence, we cannot even survive a day without classical computer. But there are something classical computer cannot do. And one such example is optimization. Optimization is the best solution of a problem among many possible solutions. Here's an example. So we are here 10 authors there. So the question is, how many possible way we can arrange these 10 authors? And the answer is 10 factorial. Although 10 factorial seems very small number, but it is actually 3.628 million possible way you can configure this author list. If I add one more author to this list, the possible combination will be 40 million. That means by 40 million different way you can rearrange these authors. If I add 3 authors to this list, the possible combination will be more than 6 billion. Meaning 6 billion, more than 6 billion possible way you can configure this author list. So again, classical computer can solve the smaller version of this problem. But when the problem is big enough of interest, classical computer either ran out of computing horsepower, or classical computer might take a longer time, or it will be difficult for classical computer to solve this problem. So we need to think an alternate computing approach, and there comes quantum computing. The first thought process came for quantum computing is 1981 by Richard Feynman, where he proposed that it's possible to build very powerful computing machine by using quantum mechanics. But the real punch came by Peter Szor. He did two things. One, he developed source algorithm which has a real application of code breaking, and also he is allowed to use fault tolerant quantum computing. And thereafter, many theorems, many research came up. For example, UCSB Google did a lot of research, and IBM and Rigetti started making cloud quantum computing. So you can basically work online and study quantum computing through a quantum computer. So we can say that quantum computing is transitioning from scientific curiosity to technical reality. One of the most important application of quantum computing is for national security. So US government stepped in. Not only US government, several other governments from different countries also stepped in. Big companies like IBM, Google, Intel, Microsoft involved. There are a lot of small companies are also coming up. And one of the major application of quantum computing is towards information security, which is basically driving the worldwide investment. So today I'll talk about a little bit introduction, and I'll talk about our approach and discuss a little bit on multi-chip module, flip chip qubit. Then I will compare superconducting versus semiconductor packaging, and then at the end summary. So classical computers are based on classical bits. It can be a transistor, it can be 0 or 1 or sequences of 0 and 1. It's a discrete and deterministic, meaning that if you set it as 0, it will measure as 0. If you set it as 1, it will measure as 1. On the other hand, quantum computers or quantum computing is based on quantum states. It's the superposition of 0 and 1 which makes quantum computer so powerful. But it's a probabilistic measurement. So if you have identical sets of measurements with 50-50 superposition of states, then half of the time you will measure as 0 and half of the time you will measure as 1. So quantum computers encode information in a fundamentally different way than classical computers. For example, if you have a 1 qubit, it can be superposition of 2 states. If you have 2 qubit, can have superposition of 4 states. For 3 qubits, it will have superposition of 8 states. So this superposition of states allow quantum computer or allow quantum parallelism, meaning because of the superposition of states, you can do many calculations simultaneously. So by the time you'll have 50 qubit, the number of superposition states will be 2 to the power 50, and which is good enough for a large supercomputer. But again, these are perfect qubit. If you go to any technical talk or any press release, there's a quantum race or quantum space race going on. IBM is working on 50 qubit system. Intel is working 49 qubit system. Google is working on 72 qubit system. Again, quantity is important. You need the heavy lifting. You need quantity to do the computation. But the number one thing is not quantity, it's the quality of the qubit. The qubit quality will determine how many gate operations you can do within qubit lifetime. The qubit lifetime defined as coherence time, the time at which qubit is in quantum mechanical state. But unfortunately, due to environmental interaction, the qubit started losing its quantum mechanical states. So the question is how many qubit operations you can do within qubit lifetime to do the quantum error corrections to sustain computation. And for the most lenient code, it's going to be 10 to the power 3 operations within qubit lifetime. Here is a coherence time plot, and here you can see different type of qubits, and these blue dots are indicating basically the qubits fabricated by Lincoln Lab. And you can see Lincoln Lab fabricate very high quality superconducting qubit with coherence time 50 to 100 microsecond, which is well above the lowest threshold for quantum error corrections. So we are fabricating high quality superconducting qubit. So our objective is to develop a 3D integration approach which is not only scalable but also compatible with qubit design and fabrication so that it can maintain qubit quality. So why do we choose 3D integration? One of the reason or one of the example is that here's a 5 qubit array, and you can see this orange colors, these plus signs are basically qubits, and rest is control and readout electronics. So the question is how to increase number of qubits, and one simple way is just increase the chip size. And with this process you can probably make 100 qubits or so, but beyond 100 qubit the wiring is going to be so complicated, you need to cross the wirings. So beyond 100 qubits, the only way you can increase the qubit density is by increasing or by relegating the routing and readout electronics to the third dimension. So our approach is very simple. You fabricate individual chips. For example, over here, you fabricate qubits separately, interposer separately, and MCM separately, and then join sequentially and interconnect with superconducting indium bulb. The advantage of our process that you are fabricating individual chips separately, so you can optimize independently. The one chip fabrication will not impact other fabrication yield. Second, you are using interposer, which is not only allow the wiring density, but it also isolate qubit chip from lossy MCM dielectric. And the third point is pretty much the first point, but what I would like to say that because you're fabricating individual chips separately and then joining, so you have no opportunity that you need to fabricate best superconducting chips, but also you have opportunity that you can take any outside superconducting qubit which has produced very, very high coherence time. So you have that opportunity to take best possible qubit and combine them together into a 3D architecture. Not only that, You can also have opportunity, let's say it's a multi-qubit system, you want to put 2 qubit chip together with 2 different foundry process, you have that opportunity now. You can do it because everything you are fabricating and optimizing independently. So here's the flip chip bonding scheme. We have to do 3-stack bonding, but before that we would like to evaluate flip chip qubit, because qubit is very sensitive to the fabrication process, and qubit use Josephson junctions, which is a 1 nanometer oxide separated by 2 superconducting metals. Josephson junctions are the building block like transistor in CMOS for making active superconducting circuits. So the first step is to demonstrate flip chip qubit and show that there is no degradation due to flip chip process. Second, you take the interposer with TSV and see the TSV surface is impacting qubit performance or not. And then at the end you do the 3-stack. But when you do 3-stack, you will see there are 2 different type of junctions we are using. One is on the qubit side, it's called shadow evaporated junctions. And other one is on the MCM side, we call it tri-layer junctions. So we are doing 2 different type of flip chip bonding scheme. One is called MCM approach, where MCM is attached to a superconducting chip which has a tri-layer junctions, and other one we call a flip chip qubit, which is basically attached to the qubit chip is attached to the interposer. So let's start with MCM flip chip process. We are working with many collaborators, and the way we work, it's kind of turnkey solution. So you submit the physical design and we'll deliver you the final product. So the way we work, you submit the physical design, we'll do the wafer layout, we'll do the SMCM fabrications. We use eyeliner lithography with 3 micron via and 0.8 micron feature size. We also can fabricate the CMOS chip or superconducting chip. We have a foundry process, and then we can assemble 2 together. With our process, we're regularly delivering 35 micron pitch flip chips, and maximum chip size is about 100 millimeters square. We can do in-house testing, RF and DC test, and also we can do module level testing. But in most of our cases, we send the final product to the collaborator and they do the final module level testing. Here's an example. Here's the SMCM design, and then you fabricate the SMCM and then bump the MCM and then bond with multiple chips. Here's a 16 chip MCM where we put 16 5mm by 5mm chips. It's called JJ chip, and the junction size ranges from 500 nanometer to 1500 nanometer. And here we bond 1 chip at a time. And what we found, this is the fabrication or attachment process over here, that you start with MCM wafer and then bump the entire wafer, and then you dice in individual MCM and bond with multiple superconducting chips to create multi-chip module or system in a chip. We are using indium bumps over here because it produces very low resistance in the range of nano-ohm. It's ductile in nature, cryogenically stable, and the melting point is about 157 degrees Celsius, which is good enough for MCM reflow process. The advantage of our attachment process, we are depositing indium only on the MCM side. So this gives us ability to select a known good chips from various suppliers, because you're not putting bump on the chip side. Or in other words, you also have a possibility to combine multiple chips fabricated in different foundry process and combine all the chips together to the MCM and create next generation system in a chip or multi-chip module. We have studied the junctions behavior with flip chip process, and what we found that room temperature study shows that the junction